Hi everyone, this video is on lesson 6 of the sound and light scheme of work, and this is about sound wave traces, as the title suggests. What's really important here is that we are covering exactly the same concepts as we covered in the previous lesson, only we're adding a layer of abstraction because this time we're going to represent the difference between a low amplitude and a high amplitude sound and a low frequency sound and a high frequency sound. We're going to represent the difference not with diagrams of particles or what's going on in terms of the tuning forks, but we're going to represent them with graphs with sound wave traces. And it's worth saying, if you've ever spoken to me about the curriculum, you'll know that I try and avoid maths wherever possible in the in Key Stage 3, because I don't want this to become kind of an exercise in doing maths without actually understanding the physics. So this lesson is not really about kind of making calculations from graphs or anything like that. It's very much just being able to get the general shape of sound wave trace graphs, so that when we get to GCSE, students are ready to look at graphs more accurately. And for example, I don't know, look at the time period and use that to calculate frequency or whatever. At this stage, we're just looking at the general shape, and I think that's fine for Year 7. So what I'm going to do is I'm going to refer back to the examples that we looked at in the previous lesson, and I think it's worth quickly recapping. So the first thing we did is look at amplitude. We took the same tuning fork. First time we tapped it. Second time we whacked it. And hopefully, and again you can show them these vibrations here like this, hopefully what students will remember, but it's worth going back to your previous diagram. This is why it's good to keep your old visualizer diagrams handy, just to show them what's happening. So if I just get rid of the frequency stuff here. But what we saw was that when we tapped it, we got these small oscillations or a small disturbance. When we whacked it, we got large oscillations or a large disturbance. And that's why we had a quiet sound and a loud sound. What we want to do now is map that onto the corresponding sound wave traces. And usually I would say, whenever you draw stuff in science, get students to draw with you. I know not everyone agrees with me on that. In this case, I would say actually, from experience, it's probably not worth getting students to draw with you. Just get them to watch, because drawing these accurately is really, really difficult. And on the plain paper that I've got in this book as well, I'm probably going to make a mess of it. But anyway, let's have a go. So if I draw something like this, so I'll maybe make it about that long, and then I'll do another one over here. I should have labelled these as the tap and the whack as well. Again, very technical terms there. So I've managed to find enough room. Note here, I'm not worried about what's on the axes, because this is more about getting the general shape rather than it being an accurate plot here. So I'm not actually going to worry too much about what's on the axes, but I might tell them that this is the displacement of the end of the tuning fork, and this is what's happening over time. But to be honest, yeah, I think just at this stage getting the shape is pretty good. So what we wanted to illustrate is when we tapped this one, this didn't vibrate that much. So what I could do if I was plotting the size of the displacement, well, what happened is as it went upwards like this, it eventually got to the top, and then it started to go downwards like this. So if I plot the position of one of these oscillating tuning fork prongs over time, I get something which will be familiar to any science teacher, but not familiar to students. I'll get something like this. And this might take a bit of explaining, and you might need to do quite a bit of hand waving, or again, animations are good for this as well. But what they need to see is the link between how this thing was moving. So when we tapped it, we said it was not moving that much, it was just moving a little bit. So you get this kind of little displacement like that. And what I can do then, we sort of associated our previous diagrams last lesson with these words amplitude and frequency. But now I'm going to put something a bit more accurate here. I'm going to say the maximum distance, or the maximum disturbance, or if we're going to use the perfect language, the maximum displacement of the tuning fork prong is from where it started to the maximum place that it got to. And that is what's called the amplitude. And it's worth me writing here, and I should have done this at the start, that this is the tap, and this one over here is going to be the whack. And again, you might want to question students on this, or you might want to dive straight into just telling them about it. But the point that you want to make is, if you tap it, you've got very little movement. You can see a tiny bit of blurriness around the edges there, but that goes pretty quickly. Whereas if you whack it, hopefully you can see much more blurred edges. Actually, the tuning fork is moving a lot more. And we can represent that by saying, if we were to plot the same thing, and this is where it gets difficult because you've got to keep the frequency the same, but if you plot the same thing, then you're going to get something like this. You're going to get a much bigger disturbance. So you get something that looks like this. Now, I've really tried to keep the frequency the same, because what you don't want to do, the absolute worst thing you can do here, is make a mess of this and kind of do it, you know, wider as well as bigger, and then students are thinking, oh, well, those wide stretched out waves, they're the loud ones. What you need to draw students' attention to is the difference between these two, between the tap and the whack, is to do with the different amplitudes. So you could label this, that distance there is the amplitude. But again, I'm not even that bothered at this stage because it's not key stage 4. I'm not going to use this to calculate the actual maximum displacement. What I'm interested in is to get the general shape. Those tall waves are loud sounds. Short waves like this are quiet sounds. And again, if I do concrete to abstract back to concrete again, I might say, well, the tap, because I've got this small amplitude, that gave me a quiet sound. Whereas the whack, because I got a large amplitude sound wave, I got a loud sound. So hopefully you can see I've just done the exact same thing that I did in the previous lesson. This time though, I am adding a layer of abstraction by representing this as a graph. Now I might do the same thing. In the last video we looked at the large fork and the small fork. I gave a very well, I still think it's a bit of a dubious explanation, so I would love to be corrected actually on that. But anyway, I gave an explanation in terms of kind of how far each prong has to move to do a complete oscillation, and therefore the larger one has to move further, so it takes longer, and therefore it's got a lower frequency. Again, what we're going to do in this lesson, instead of doing it like that, and I'll try and keep the format exactly the same, let's start with the let's move down here. So let's start with the large fork. Small fork, and again I would recommend you refer back to the diagrams that you drew previously. But what I'm going to try and do is show the difference between those in terms of their different sound waves. So let's do that like this. So I'm going to try and keep everything as it was, and you will see from the difficulty I'm having here why I don't think it's a great idea to get students doing this diagram in their books, because it's quite tricky. And again, I'm not putting anything on the axes deliberately, which I know a lot of science teachers are going to be horrified by, but the reason is, at this stage, I only really care that students get the shape. I would kind of like them to have an idea of what these axes mean, but it's not my main focus right now. If they come away not being able to recognize the shapes, then I'm pretty happy. So what I want to do is show students that, and remind them, and again, this is hard to illustrate into the visualizer, but what I said in my diagrams before is, because these have further to go, they don't do it as many times a second. So if we have the same amplitude, so we're going to try and keep those, and I might just give myself some guidelines just to kind of just try and keep it consistent. So I'm going to do something like this, like that. If my waves have the same amplitude, the point is here, because it takes longer to do a complete oscillation, this one is going to take longer. And now I'm exaggerating this. Obviously it's the same fork as before, so maybe that's going to add a layer of confusion. So I'll leave this to you to do a better job than me. But what I want to do is illustrate the difference between the large fork, which has this low frequency, and then the small fork, which has this much higher frequency. Now, again, as I've said, I've not done the best job here, but the main thing that you want to draw students' attention to, well, there's a couple of things. One is that if we whack them at the same level of whackness, I'm running out of words to describe this, with the same intensity, even though they are different different lengths and therefore make different sounds, they will have the same amplitude. So you could draw students' attention to the fact the reason you put these guidelines in is that all these waves have the same amplitude. But what we're interested in here is the difference, and maybe it would be worth me striking these together just so we can illustrate. The difference between these two sounds, if I get them the right way around, is that one oscillates more quickly. And the reason for that is because what I can label here is this property here, or you might want to label it as this property here, wherever you want to do it. This is the time period, okay? This is the time period, not the wavelength, because I'm really doing a trace over time. I'm looking at the displacement of the end of the fork over time. But this has a long time period. This time period is much shorter. And this corresponds exactly to what we drew in the previous, I'll just put time here. Time, and I'll put time period to make sure we get it right. This is the time period here. This corresponds exactly to what we talked about here. Because look what we said here. We said this one has a longer time taken to do a complete oscillation than this one. This one has a much shorter time taken to do a complete oscillation. That's why this one can oscillate 256 times every second. This one can oscillate 512 times every second. So what we're doing is trying to map that kind of concrete picture that we gave last time onto this more abstract picture. And effectively, what we therefore want students to be able to do is associate the large fork, which has the long time period, with a low-pitched sound. And the small fork, which has a small time period, with a high-pitched sound. Now this is really difficult stuff. And what we're attempting to do here is not just get them to memorize squashed waves have a high-pitched sound, which is pretty easy. And let's be honest, if that's all they can do by the end of this lesson, that's a decent result. But the reason that we've taken our time to do this, and the reason these lessons are laid out as they are, is because we really want the students to have a sense of how the pictures we drew in the last lesson, and I'll just return to them one more time, these pictures to do with what's actually happening with the tuning fork moving through time and space, how do those pictures relate to these pictures? Because it's only if they really get how the kind of concrete pictures relate to the abstract wave traces that we can really say they understand what these graphs are representing and really what we mean by amplitude and frequency. So the last thing to say is it's probably worth saying to students that if you've got this long time period, that means you have a high frequency. So we might want to add something in here about high frequency. So time period, this would be a low frequency. This one, because it's a shorter time period, would be a high frequency. And again, it's just another way of reinforcing what those two words mean and how that relates to the sound. Again, in my experience, this lesson, it will take you quite a while, but it's worth persevering and really spending the time making sure students are happy with what you're talking about here. Now, there's loads and loads of examples in the slides. The first set of questions is about identifying these sorts of things and really doing what we've done here. In the second one, it's about getting them to draw their own wave traces. And if this takes more than one lesson, I think that's fine. I think it's worth spending the time really getting students thinking rather than just rushing through it. Because if they can really think about this stuff in the way that we want them to, then when we get to year 11 and they're doing all the wave calculations and they're trying to understand those different pictures to do with the electromagnetic spectrum, they're going to have a much clearer idea of what's going on if we've put the time in at Key Stage 3. So that is it nearly it on sound waves. It's certainly it on wave traces. In the next lesson, we'll finish off sound waves by looking at echoes.